Creation of a high-temperature plasma through merging and compression of supersonic field reversed configuration plasmoids. Number 3. FRC fusion scaling. The fusion reaction rate dN dt for dt fusion system is given by where n is the number density of species alpha and sigma v is the reaction rate parameter for the fusion action of interest for a plasma with ion temperature T. It will be assumed that n equal 1/2n, where n is the total ion density for pulsed systems such as the IPA-based FRC device considered. Here, the relevant quantity is the total neutron yield per pulse. Equation 5 should thus be integrated over the lifetime of the plasmoid and then multiplied by the repetition rate R to obtain the neutron flux for the purpose. Here it will be sufficient to multiply the left-hand side of equation 5 by the energy confinement time. The energy confinement is typically 2/3 of the particle confinement time, and the particle confinement for merged FRCs was found to be roughly a factor of 2 better than the expression in equation 2. During the decay of the FRC, the plasma density and temperature are maintained as the product must be in radial pressure balance with the external magnetic field. See Figure 1. The total fusion energy provided by the DT reaction is E equal N. This includes an additional 4.8 MeV from the lithium fusion in the blanket required to obtain a new triton for continued operation of the reactor. With this, one can write for the FRC. For the highly elongated FRC, the volume can be approximated VOL equal pi R to the power I for temperatures between 10 and 20 keV. The usual approximation for the DT fusion cross section is delta V 1.1 cross 10 to the minus 31 T to the second power. It is clearly desirable to operation at the upper right limit in magnetic field pressure, as this maximizes the fusion yield, since increasing the ion temperature comes at the expense of decreasing N for a given magnetic pressure. See equation 1. There is thus no advantage in seeking higher ion temperatures. In fact, there is a disincentive in that the FRC lifetime also decreases with decreasing N. It turns out that for ion temperatures in the range of 3 to 12 keV, the range anticipated for the optimal operation of the IPA device fit to the cross-section is better approximated by delta V equal 4 cross 10 to the minus 33 power T to the 2.6 power electron volt as is indicated in Figure 6. Figure 6 nuclear cross-section for DT fusion and approximate fits over range of interest for pulse FRC fusion. Given the FRC confinement scaling and the ion temperature within this range, the neutron yield is essentially independent of the ion temperature. More precisely, the increase in fusion across section at higher temperature is offset by decreased density and FRC lifetime at a given compression magnetic field, while the physical dependencies for all terms in equation 6 have been identified. It is worth introducing quantities that are primarily determined by the device parameters that can be changed and optimized. The fundamental parameters in this regard are the compression magnetic field B, the compression coil radius R, and the magnitude of the FRC toroidal flux phi, assuming that the current profile is similar to the rigid rotor profile commonly inferred by observed pressure profiles. The crossed toroidal flux along with B and R in turn determine the plasma radius R. With equation 7 for the FRC radius and solving equation 1 for the density along with the appropriate approximation for the DT cross-section as stated above, the FRC fusion energy per pulse from question 6 can be written in terms of the experimentally controllable variables. The FRC toroidal flux and final FRC length are primarily a function of the scale of the formation sections positioned at each end of the device. See figure 2 and 3 to obtain the fusion again. Equation 8 must be normalized to the FRC energy acquired each pulse, the FRC energy can be started as employing equation 7 again for the FRC radius 1 Hz. It is notable that the gain has two dependence on the compression coil radius and only a fairly weak dependence on the FRC length. Gain contour as a function of the FRC toroidal flux and compression field are shown in Figure 7. Figure 7 gain controls as a function of the FRC toroidal flux and compression magnetic field. It was assumed that the FRC length L equal 1 meter. This is not to say that one is free to pick any radius for the burn chamber compression coil. As was pointed out earlier, there is a kinetic stability criterion which was expressed as S per epsilon smaller than 5, stating this criterion in terms of the control variables. Where the ion atomic number was assumed to be 2.5 for the DT plasma, for kinetic and or Hall effect to stabilize the FRC, the ion Gull orbit must remain a significant function of the plasma radius, either a higher T or lower pi, with a reasonable assumption for the function ion temperature. 9 kV equation 11 expresses the stability limit on the amount of toroidal flux for a given coil radius and confining field. The plot of the regions of the phi B space of Figure 7 that are excluded for various coil radial are shown in Figure 8. Figure 8 gain plot, as in Figure 7, with regions of exclusion for different compression coil radial R, where an ion temperature was 9 kV and a FRC length L equal 1 meter were assumed. It is clear that to achieve fusion gain at the lowest possible compression field, a coil radius of 0.2 meter or less is desired, with a coil radius of less than 1.1 meter, assuring kinetic stability for the largest range of both flux and compression field. There are several reasons to keep the compression coil small. Certainly, the amount of compression field energy required per purpose is thereby minimized, but perhaps more importantly, the wall along per pulse is reduced as the ratio of wall surface area to reacting volume scales as 1 R. Thank you.